Hi, I'm Jack, and I will be your instructor for this course. This course is going to teach you about the basics of compiler design. A compiler is a program that translates source code which the programmer has made, and that source code gets converted into machine code, bytecode, or another programming language. This course is based on an interpreter. An interpreter is the same thing as a compiler, except that the source code is instead directly executed. C or C++ is an example of a compiler that translates a source code into machine code. Then that machine code is directly executed by the computer. Java is an example of a compiler that translates source code into bytecode. Then that bytecode can be executed. Just keep in mind, most Java compilers nowadays use a just-in-time compiler, also known as a JIT compiler, but that is a whole nother topic which won't be covered in this course. Python is a great example of an interpreter. You write Python code, then it gets directly executed when you run it. Technically, Python is a bytecode interpreter, although you can think of it as an interpreter either way. We will be going over a lexical analyzer, a parser, and an interpreter. We will not go too in-depth with the compiler design because this is a basic course. So this is more of to get you a basic understanding of compilers. So when you go more in depth with it in the future, you will have less trouble understanding what's going on. Thank you and hope you enjoy the course. Hi, I'm Jack, your instructor for this course. I'll be going over what a lexical analyzer is. So, lexical analysis is also known as lexing or tokenization. So some people use these terms such as lexing or tokenization, which refers to the word lexical analysis. A lexical analyzer is also known as a lexer, tokenizer, or scanner. Some people don't say lexical analyzer, they just say lexer or tokenizer or scanner. These words, such as lexer, or tokenizer, or scanner, are commonly used or frequently used by people. So what is a lexical analyzer? So a lexical analyzer converts text or a sequence of characters into a sequence of lexical tokens. So pretty much we have the first input data, which is a string or a text, like let's say 1 plus 2, or like a text, and then the lexical analyzer converts that text into a list of tokens or a sequence of tokens. So you may be wondering what these tokens represent. So you'll be seeing through these examples. So let's say we get the text 1 plus 2. So our first token from the lexical analyzer is token type number and then token value of 1. Next one, plus, and then token type number 2. So you see how these tokens are actually ordered from left to right, and these tokens have a type and a value. The type could be a number or a plus. So this type kind of indicates what the data of the token is going to be. And the value indicates that data or the value, right? So token type number, we know it's a number, right? So the token value has to be equal to a number, right? So token type number, the token value is going to be a number. So this one on the very left will be token value 1. Because 1 plus 2, token type number, token value 1. And then the next token is token type plus. Now we don't need a token value. The NA stands for nothing. We don't need a token value because, of course, we already have sufficient information that the token type is a plus. Since we know it's a plus, we don't need any more value or any more data. And the next one is token type number, token value 2. It's pretty much represented in this text right here, 1 plus 2. As you see, it goes from left to right. And then now let's get another example, 30 plus 19. Same thing, token type number 30, token value of 30, and then plus, and then token type number, token value of 19. So let's say we have a subtraction sign instead, or a minus sign. It's still the same thing, except the token type will be a minus instead of a plus. So we still have the same exact things. Token type number, the token value is 21. It's all ordered correctly from left to right. Token type minus, and the token value is NA because we already have sufficient and enough information. And then token type number, a value of 54. And then same thing here, except we have the token type multiply instead of minus. This indicates again, it's a multiply sign. We already have enough sufficient information. We know that the star symbol is usually used for multiplication, so that's why it indicates by that. So let's say we have 64 divided by 4. Same thing, divide token type, token number value 4. The slash indicates it's a division operator. Now let's say we have this where we have 12 times 3 and then a white space, like a space, and then 65. So what we'll actually do is 12 multiply, right? Same thing, 3, and then since there's a white space, this is going to be a separate number, which is 65. So this is how the tokens are going to be. Token type number, token value 12, then token type multiply. We already have sufficient information, right? And then token type number 3 and then 65. So this the white space in the text indicates that these are going to be separate tokens, or these are going to be separate numbers. So remember that this is not going to be 365. This is just going to be 3 and 65 that are separate tokens. So that is pretty much it for what a lexical analyzer is and its process and its value. Thank you for watching and hope to see you in the next lecture. I'm Jack, your instructor for this course, and I'll be teaching you what arithmetic operators are. This is an important part of lexical analyzers. So, an arithmetic operator is a mathematical function that takes two operands and performs a calculation on them. Most programming languages contain arithmetic operators that are used within equations to perform a number of calculations, like Python, C, C++, Java, and etc. I will be explaining what operands are on the next slide. In a mathematical expression, there are two elements in it, which are operands and the specific arithmetic operator. In this example, the numbers 2 are the operands of this mathematical expression. The operand represents the data that is going to be operated on or changed by some type of operator. In this example, the arithmetic operator is addition. Therefore, the addition operator will operate on the operands, making it so that the two operands will be added together, and the sum of those operands will be 4, because of the addition operator. 2 plus 2 is 4. Here are the common arithmetic operators. We have addition, subtraction, multiplication, division, and the modulus operator. As you see here, there are the symbols for the operator, the meaning of the operator, and an example and a result. 6 plus 2 is 8, 6 minus 2 is 4, 6 times 2 is 12, 6 divided by 2 is 3. The modulus operator is something you may have never seen before if you have never used it. The modulus operator gets the remainder in division. Let's say 7 mod 2. Generally, the word mod is used for a modulus operation between two numbers. 7 divided by 2 is not 3, but 6 divided by 2 is 3. Because 7 divided by 2 does not equal a whole number, and it equals a decimal number instead, the modulus operator tries to give a whole number instead of a number with a decimal. 7 mod 2 will result in a remainder of 1. 7 divided by 2 results in a decimal value, but 6 divided by 2 does not. And 6 divided by 2 is equal to 3. We know since 3 is a whole number, not a decimal number, 6 works. So to get 7, we add 6 with 1, which equals 7. Thus, the remainder is 1, since adding 6 with the remainder 1 will equal 7. Here's a pseudocode example of detecting arithmetic operators. You can use this for your lexical analyzer. If you don't know what pseudocode is, basically it is resembling a simplified programming language. It is to show others how the program is designed, but it is not a specific programming language. Here we have tokens list equaling to a list right here. The square brackets indicate it's a list. A list is a data container where it has multiple values in it. Think of a group of people in a community. You can think of it like that. So for each character in text, so we're going through each character in that specific text, like let's say 1 plus 1 or 2 plus 2. If the character is equal to 1 plus the plus sign right here, we can add into the tokens list or append, or also known as add, that the token has a type of plus and the value is none. Else if, let's say the character does not equal to plus, but it equals to the minus sign, we can append into the tokens list or add into the tokens list that the token type is minus and the value is none. Therefore, once we've gone over the whole text and detected every single character, we can see that the tokens list is filled with arithmetic operator tokens such as plus, minus, and etc. You can do more detection here, like else if character equals to the star sign for multiplication, but this is just a minified or simple example. There is a Python programming lecture of a lexical analyzer. So there's a lecture where a lexer or lexical analyzer is fully built with the Python programming language to really see how lexers or lexical analyzers are built using a programming language. This is a great way to see or to build your own lexical analyzer because you'll know how to build one since you've seen an example with building one in a specific language like Python. In conclusions, arithmetic operators are important in programming languages as they define and result in necessary mathematical computations. Arithmetic operators are totally not necessary, but almost all programming languages have mathematical calculations using arithmetic operators. Thank you for listening and see you later in the next lecture. I'm Jack. Today I'll be going over what numbers are. This is specifically based on integers and not floating point numbers. I will be explaining what integers are in the next slide. So, integers are numbers without decimal points. Think about whole numbers like 5 or 10 or 20. They're just integers because they don't have decimal points. Floating point numbers, also known as floats, are numbers with decimal points, like 1.23 or 2.34. Here are some examples. Here's like an integer right here, 25, and a floating point number, 25.23. So, numbers are arithmetic values that are used in mathematical calculations, like 23 plus 10. Programming languages have different number types. So here is an example of the C programming language. Here are some common number types that are used. If you don't quite understand what number types are, they're a very basic concept. I'll be explaining more in these next slides. But for now, let's see this chart. So here's a character type right here. Char or character, unsigned character. Int just stands for integer. Short is a whole number type, and long is a very big number. So to elaborate more, a char has a storage size of 1 byte, and I'll be explaining what a byte is in the next slides. It has a value range of -128 to 127 or 0 to 255. It depends on the C programming language, but these value ranges just show that there's like a maximum value that a number type can have, or a maximum number that a number type can have. So these are what number types are, is they have a maximum integer or floating point or number value that you can't go over, or else it will cause integer overflow, or yes, an integer overflow, which is what you don't want for to happen, because it usually causes undefined behavior. But basically you don't want to go over that byte. If you would like to know about integer overflows and stuff, you can look it up online. But this is more focused on the compiler design course, compiler design. Unsigned character, it's also 1 byte, 0 to 255. 255 is the maximum value. This is inclusive, by the way, so 255 counts as well. Integer, 2 or 4 bytes, it can go up to these values right here. And then short, 2 bytes can go up to these values. And here long, 8 bytes or 4 bytes for 32-bit OS operating system, you can go up to this byte. So basically, when you're, let's say you need a really huge number, more huge than integer, then you'd use the long number type. So a binary number is a number expressed in the base 2 numeral system. So for example, 11010101, these are actually used for bytes, which I will elaborate more in the next slides. A decimal number is a number that we use every day. So expressed in the base 10 numeral system, like 255 or 500 or 600. That's just what we use every day. So to elaborate more on what bytes are, 1 byte is 8 bits, and a bit just stores a 0 or 1. So here's an example of a byte, 10101110. We actually use a subscript 2 to kind of indicate that it's a base 2, and the decimal a base we indicate it's a base 10 by the subscript of 10. Here's an example of a bit. This is 1 bit, so a bit just stores a 0 or 1, so it could be a 1 or 0, and it goes throughout the whole binary number. And this is a byte because there's 8 bits. So like 1, 2, 3, 4, 5, 6, 7, 8. See my mouse here, 1, 2, 3, 4, 5, 6, 7. As you see, if you count each digit of the binary number, you can see it has a total of 8 digits. And then each digit of a binary number is pretty much a bit. So there's 8 digits, 8 bits. So here's an example of why an unsigned character would have a value range of 255, because 8 bits is equal to 1 byte, right? So then the storage size is 1 byte. So there's going to be only 8 digits or 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. And then we know that the maximum value is you can only get to, only a bit can store 0 or 1. And 1 is the maximum value a bit can store. So when we, this in binary number equals to 255 in decimal value. So this is why the value range is 0 to 255. I'll be explaining how to actually convert binary numbers to decimal numbers. So here's an example right here. So let's say you have 1, 1, 1, 1, 1, 1, 1, 1. This is a byte, so 8 bits, and it's a binary number. So we usually read binary numbers from right to left. And here's an example. So the bit or digit in the very right is equal to 1 in decimal value. So this in decimal value right here is actually just 1. And then how do we count further more of the binary or the bits to create a decimal number? We actually, right here with the decimal value right here, we every time we go to the left by one, every time we go to the left by 1 digit or 1 bit, we actually multiply by 2. So then we get 1 times 2 times 2 times 2, then 4, then 8, then 16, then 32, then 64, then 128, because all these are being multiplied by 2. So think about like base 2 system. You multiply by 2, right? Because it's base 2. So 8 times 2, 16 times 2, 32 times 2, 64 times 2, 128. And then we do that every single digit, every single time we go from right to left. So right here, and then go left, and then go left, and the decimal values just get bigger. So if that makes sense. So now we just add these decimal values together. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and you get 255. Just remember the very right, the first ever decimal number is 1. Always remember that. And then every single time you go to the next digit or the next bit, it's multiplied by 2 on the decimal value, so it becomes 2. And then you use these values to actually add them together to get the actual decimal value. So let's say there's a 0. So think about 1 as a yes and 0 as no. 1 is like true, 0 is false, 1 is valid, 0 is invalid, if that makes sense. So right here we have 1, but here's a 0. So then this decimal value does not count. So we keep doing the same exact thing as we did on the last slide, but instead, so like we still multiply by 2 and all that, but if it's a 0, then this decimal value does not count. This is represented by the strike through. We don't count this. So we still count like the decimal values that have a 1. Like here, so it'd be 128 plus 32 plus 16 plus 4 plus 1. But then these values with the 0 does not count in the addition. So we only add the ones with the 1. We only add, so 128 plus 32, and then we get 181. So 1 byte or 8 bits is not big enough for a number over 255. So this is why there are the larger number types like int or integer and C that can fit 2 or 4 bytes. So we can even add more binary numbers. And with those numbers, we can actually multiply by 2 on the decimal values, right? So it can be like 128 times 2, and then 256. And then further on, multiply by 2 even more, which will create large enough numbers. So these bytes, or there are more bytes to fit in. So here's an example of how a lexical analyzer or scanner, or you can call it a scanner or tokenizer, can scan through a number and just a general mathematical expression. So the scanner, what it does is it checks the character, right? And then, oh, it's a 1. So we add 1 to our token right here, token value. And then, oh, it's a 0. So we go to the next character, now we see it's 0. And then we go to the next character, now we see it's a 2. So now we have 102. We detect it's a white space, or we detect that it's not a digit, it's not a number or digit. So then we know that the token is 102. This is we can use a white space to indicate that it's not a digit, right? So this white space is not it doesn't when the scanner scans this character, it's not a number, right? It's a white space. So now we go scan this character, it's a plus, right? And then we can automatically assume it's a plus, right? Token type plus, token value is none, because we already know enough information that we don't need further data. Scan through, now we have 3, 2, scan through each character, and then now we have the token value 32, and then now we have the tokens that the lecturer or tokenizer have created. Here's a pseudocode example of detecting numbers. So right here we have like tokens list, we can add in tokens, and we have a current number. So these are 2 variables, and then for each character in text, if the character is a digit, we actually add it into the current number, the character. So like for example, let's say we have the character 1, it will append the current number to the string. This is called a string or text. Then the current number will be equal to 1. And then let's say the next character is 2, and then we add into that current number, which is 12. And then let's say it's not a digit. So basically what we're doing is we're accumulating this current number and then we're making it to the number by the, if the character is digit, then we add into the current number, 1, 2, blah, 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 of all the digits. If it's not a digit, we append to the tokens list of the variable, and then we append token type number and a value current number, and then after that we make current number equal to, like, it's not a, it's text, but it's an empty text or empty string. It doesn't have any numbers in it. So if this sounds a little confusing, or if you've never seen pseudocode before, please don't worry. Think about this scanner scenario I showed you with the on the last slides with the tokens, with the arrow symbol, and then going through the characters. Think of it. It's just that's the same concept that's shown in the pseudocode, but instead it's shown in like a programming in the sense instead of, so you, if you understand the scanner part of scanning through each character, you're totally fine. You don't have to really understand this. This is more for people who actually program, who want to create a lecture. There's also a Python programming lecture of a lexical analyzer. This is able to show you how to create a lexical analyzer officially with the Python programming language. And then this is pretty much it for numbers. In conclusion, numbers are very necessary to know, and binary numbers, decimal values, bytes, these are very essential to know to uh, ultimately understand what numbers are and their purpose in a calculation or an expression. Thank you. Hello, I'm Jack, your instructor for this course. I'll be going over I'll be teaching a Python programming lecture of the lecture. So to begin, the main.py file is just a read environment, read, evaluate, print, and loop environment. So it's just REPL. This is an example of we have a while true, and then we make an input, calc, text strip equal, and then try except a runtime error, so we can actually throw a runtime error. So here's the lecture code. So before we make the lecture, we make a tokens code. So there's a token type right here. This is a TT type stand for. So TT stands for token type. And we have the number type, the plus, the minus, multiply, divide, modulo. You can pretty much make this like an enumeration kind of thing. And then we also make a utility function where we convert that token type operator into a character. So like let's say it's type TT plus, we return the plus character, the minus character, etc. Here's the class token. We have an in constructor method where we can create the class token, and then it's a type, which is can be one of the token types, and the value, which is a float, optional float, because we're gonna have only float values, right? So the float can be none, because let's say it's a token type plus, then we don't need a value, right? So, and then we can make a representation or to where we can just pretty much make it so we we show the token type, so number for example, and then if the value is nothing, or if the value is not nothing, then we add into the token representation of the colon and then the value. So then let's say we made a token value of, or a token of type number and then value of 4, then it's going to return number colon 4. So it's just pretty much to debug, pretty much that's what it's meant for, to kind of see what's going on. So then what the lecture does is we're going to actually just make an initialization method or constructor. Index equals 0. We, of course, going to get a text. Current character is none for now, but there's going to be a character, and then we advance. So what the advance does is we're pretty much in updating or incrementing the index by 1 and then getting the next character. So what we're doing is we're going to the next character every time we call the advance method. So let's say it's 1, 2, 3, and we're on the first character, which is 1. We call the advance method. Now it's on 2, advance method 3. So we pretty much just index that self-index, get current character, and increment that by 1. So now we get tokens. So while the self-current character is not none, self.current, if it's a space, we ignore that, so we advance to the next character. If it's a dot or a digit, we actually append to the tokens list. to get the number. So the tokens list is just a list of tokens that we're gonna actually return right here. And then right here we have the get number method where it's number as self current character dot count and advance. While self dot current is not none or it's dot, we add dot count. If the dot count's over one, we actually break the loop. And the reason why is because a decimal only has one dot, right? It doesn't have more than one dot. And then number, we increment that current character. If the number first character of the number is dot, we just add a zero in front of that dot. If the last character is a dot, we add a zero at the end and then return that number. And the same thing with these other, if the character is a plus sign, we just advance and then return that token and make these tokens right here for the correct characters. And then we raise a runtime error. There's an illegal character, so a character that we've never seen before. Or it's an unknown character to a math. And that's pretty much it for Elixir. You can just pretty much call the Elixir method to get the tokens, and then you can print out the tokens. That's it for the Lexical Analyzer Python programming lecture. Thank you. I'm Jack, your instructor for this course. I will be going over what a parser is. So, parsing takes input data and builds a data structure, usually an abstract syntax tree or a parse tree. So what the parser does in this scenario is it actually takes those the input data, which is the lexical tokens or the sequence of tokens, and then we actually will build a parse tree, an expression tree, a binary tree, an abstract syntax tree from that lexical tokens. So parsing is based on a rule set called grammar. So basically, what this will do is when we parse a lexical tokens, we will see if the tokens are in their right place or if there's parentheses or there's correct stuff going on. For example, 1 plus 2 is correct, right? But let's say we did plus 1 plus. So see how that's incorrect? Plus 1 plus, there's missing operands or there's missing numbers in between those in between the addition operation. If you don't understand, I'll be explaining it in here. So like let's say think about the grammar of the English language. This is wrong right here. Hello, I'm Jack. See how the grammar is wrong here? That's what the parser will help detect is they'll see there's a missing comma and then there's a missing apostrophe here. Like this is correct right here. This is what the parser wants. This is not what the parser wants, and then it will probably error due to this since this is incorrect. So just basically you have to have the correct grammar. Here are some examples of expression trees, and for the grammar we will be going more over it in one of the next lectures, which is the grammar part of the parsing. So here are some examples of expression trees or binary trees. And so here is 1 plus 2. So we see how we have this like tree. There's a parent node. These are called nodes. These nodes are just like individuals, like right here with the individual data. So like number and then a value 1. And then here's another node. Here's a number, value 2. And then here's a node, which is the addition operation. And then the node has 2 children. These are children. This is the parent node. This is the children node right here on the bottom. The orange circles are the children node, and the blue circle is the parent node. So this is 1 plus 2. Here's another example. Here's the number 4, value 43 minus 5. And see how these are also ordered? These trees are also ordered, right? So it's not like 2 plus 1, but it's 1 plus 2. There's also here, here's why so right here we have 1 plus 2 times 3. So we see how the child of the add node is actually the multiply node. And the reason why it's this is because there's 2 times 3, right? So we this is due to operator precedence or order of operations is, and a lot of these topics that I'm saying like operator precedence or binary trees, I will be explaining these in the next lecture, so please don't worry. So anyways, it's like 2 times 3, and then this will be equal to 6, right? And then we need to make sure that we multiply these 2 times 3 before we add 1 to it. So that's why it's add 1 and then to multiply. But the multiply has to be done first before it can add 1, right? So you'll see more of this on how this makes sense. Here's also one, but instead with parentheses, we're indicating that we want to add 1 plus 2 first before we multiply 3, right? That's basic calc math. So we see we have the multiply, but 3 times we have to actually add first right here to get the result here, and then when we get the result, we can multiply these two together. So if order of operations, or it's called operator precedence, is applied, then it matters in the binary tree, right? So right here, operator precedence matters, is because 1 plus 2 has to be first, and then we can multiply it. There's also a Python programming lecture of the parser. It's specifically a recursive descent parser. In the next lecture, you'll see what a recursive descent parser is, or what it's specifically meant for. But we're making a type of parser called a recursive descent parser. This is it for parser. There will be more of the topics will be explained in the next lectures. In conclusion, parsers are very necessary. They're pretty much one of the biggest building blocks of a compiler or an interpreter. Thank you for watching. I'm Jack, your instructor for this course. I will be going over what a binary tree is. So what's a binary tree? So a binary tree is a tree data structure. It's a type of tree data structure where each parent node can have at most 2 children. So it's kind of the expression trees or the binary trees that I showed you in the last lecture of what a parser is. And those are pretty much what binary trees are. There's also other types of tree data structures. One is an abstract syntax tree, or it's shortened as AST, which is a tree representation of the abstract syntactic structure of a text written in a programming language. In basic words, this is pretty much used for like actual big programming languages like Python or C, C++. It's basically the more complicated programming language that usually use an abstract syntax tree. It's the abstract syntactic structure of text. So let's say it's like x equals 5. It'd be the variable x and then equals and then 5. That's pretty much what an abstract syntax tree is. It's like the English language like probably generates an abstract syntax tree, right? Please don't get too in depth. We're not going to go too in depth with the abstract syntax tree. We're going to be going more in depth with the binary tree. So please don't worry if you're not 100% sure on what the abstract syntax tree is. And it's used for programming languages, but it's more or less the same as a binary tree pretty much. It's the same thing except it has more than 2 children. But usually it's the reason why I explained that it's used for like a big programming language is because you're gonna have to have more than 2 children, right? When you're have a really big programming language that is not as simple as like math, like 1 plus 2, where you can just have 2 children. So abstract syntax tree is more for the complicated languages because you need more than 2 children. And yes, both the abstract syntax tree and binary tree have nodes. So here's an example of a binary tree of 1 plus 2 times 3. It's an example of the mathematical expression here, as we explained it, 1 plus 2 times 3. So to point out, these are the nodes right here. Like right here, these are the nodes, like number value 2 is a node, number value 3. It's pretty much the circles are the nodes, pretty much like the yellow circle, each circle is a node. And each node has data. So like add data or data of the number value 1. And here's another example. Here's the parent node, as you see in the screen, and then here the child nodes, so the children. Usually the children nodes are just the one that are on the bottom and the parent nodes on the top. So each node has 3 elements. So there's a data value, like for example, the number is a data value, the value 1 is a data value of the node. There's a variable to the left child node, and there's a variable to the right child node. So this add node probably has a data or variable or a pointer to the left child node, so then it can, it could probably see the data of the left child node if it has to, right? Because when you add something, you need to know the numbers, right? So then you have to reach out to that node or to that variable of the node and be like, hey, can I get the value 1? And then you do the other one, hey, can I get the value of 2? It's just pretty much communicating with each other at this point. So a node with no children is called leaf node. So a leaf node is, here are the leaf nodes. They don't have any children. So a node does not have to have children. It can be by itself, right? It doesn't have to have a variable to the left child node or to the right node, child node. It could be nothing. But they could have data still though. So this one still has data, number value 1. So leaf nodes can have data, but they just don't have children. So here's a pseudocode of making a binary tree, or binary trees, yeah. This is just pseudocode again. It's probably different in your language or programming language. But here's value, nothing, left child, nothing, right child, nothing. You can think of nothing as like null or nil or none. And then here, like leave number 1 node, we make a structure node of the value 1. And then leave number 2 node, value 2. And add node, structure, value add. We're saying it's of add value. And then left child is the left number 1 node, and the right child is leave number 2 node, and then we will display the add node. So I've also made a representation of what it will look like when you display that add node as if you were creating an actual node in a programming language. So let's say we display the add node. This is what the pseudocode binary tree looks like. So this is the parent node, which is the add node variable, the child node, which is the leaf number 1 node variable, and that child node is leaf number 2 variable, leaf number 2 node variable. So you see how right here I'm defining the variables. If you would like to get more into it, you can either look at the Python programming lecture of a recursive descent parser, or you can just look at the Google Slides that I've put in as a resource link. And yes, that is all for what a binary tree is. They're very essential because they're the reason why you create a parser, right? Because you're producing a binary tree at the end of the day. Thank you for watching and hope to see you in the next lecture. I'm Jack. I'm your instructor for this course, and I will be going over what a operator precedence is. So operator precedence isn't as hard as you think. It's just order of operation. It's like saying 1 plus 2 times 3, and we know we multiply it first. It's like PEMDAS. If you've ever heard of PEMDAS, it's the order of operations. So we do parentheses first, and then exponents, and then multiplication, and then division, etc. And so then it's basically a collection of rules about which procedures should be performed first in order to evaluate an expression. So think about like just pretty much rules where one calculation being performed or procedure has higher priority than another procedure, so that procedure gets executed first. So basically it's some things have higher priority than others, so then those higher priorities are first in line, right? So they need to be done first before the lower priority stuff is done. So higher precedence just means higher priority, and lower precedence just means lower priority. So I'm going to be going over operations. So what is a binary operation? So it's a mathematical calculation performed on 2 elements or operands. You learned this in arithmetic operators to obtain a third element. So in basic terms, binary operation is just an operation with 2 operands or 2 numbers. Unary operation is an operation with only 1 operand. So it's like binary operation, except it's just 1 operand instead of 2. And you're like, what do you mean? I'll be giving you an example. So here's an example. 10 plus 20 is a binary operation, and then negative 10 is a unary operation. Why is that? Because the binary operation has 2 operands. The 2 operands are 10 and 20, right? and the addition operator is operating on those two. But the unary operation has only one operand, which is 10, right? So the negative sign or the minus sign is the operator, but it's only operating on the 10, right? Because 10 is the only operand. Unary operation generally has higher precedence than binary operation. You can literally customize your programming language and make it so unary operation doesn't have higher precedence. So just remember, generally, like in math, for example, usually has higher precedence than binary operation. So negative 10 would be evaluated first before adding to 5. That's why negative 10 plus 5 is equal to negative 5, right? Because the negative sign is in priority, so it just makes it negative 10 plus 5 and then negative 5. Here's an operator precedence example of like a basic mathematical calculator rules. So you see how in precedence over number 1 is plus and minus, the unary addition and unary subtraction. So like negative 5 or positive 5. Those are the first in order or first in line to be operated on. And then the second is multiplication, division, and modulo. So like let's say 1 times 2, it's going to be operated first. And then the third in line is addition and subtraction. So like 1 plus 2. You'll see an example of how operator precedence would work here in the next slides. So if the operator has the same precedence, it usually just evaluates from left to right. So let's say 1 plus 2 times 1 plus 2 plus 3. Then it would just evaluate from left to right. So then 1 plus 2 plus 3, and then 1 plus 2 is 2, the 3, and then 3 plus 3 is 6. So the answer would be 6. It's just evaluating from left to right if the operator has the same precedence. So here's an example of 10 plus 20 times 30. 20 times 30, multiplication will happen first because the operator's star sign, which is used for multiplication, has higher precedence or priority. So then 20 times 30 would be evaluated first. And then 10 plus 60 addition will happen second because the operator plus has lower precedence or priority. So then it would be 10 plus 60, right? And then 70. That's why the answer is 70. Here's a more example. So this has the same addition operators. Since these operators have the same precedence, priority, it evaluates from left to right. So 10 plus 20 would go first. And then 30. And then since these operators have the same precedence priority, it evaluates from left to right. So then 30 plus 30 and then 60. So here's the same thing. Minus and addition has the same priority or same precedence. So it just evaluates from left to right. And then 10 minus 20 and then negative 10 plus 30 and then 20. And then same thing with like multiplication or division. It goes from left to right because these operators have the same precedence or priority. So it would be 10 times 20, 200. 200 divided by 80 is 2.5. So here's is why, for example, here we can indicate operator precedence here is because in order to add 1, we actually need the result, the child node, which is the multiply node from the add. So the add node is the parent node, the multiply node is the child node of the add node. And in order to add 1, we actually need to go through the multiplication first, 2 times 3, and then once we get 2 times 3, we can finally add that to the child node, right? So here's why it's multiply node is more under level and it's a child node. So the addition is dependent on that multiply node. That multiply node needs to multiply 2 times 3, so then we can add it to 1. The same thing with unary negation. Negative 2, right? So then 1 plus negative 2, and then yes. Here's the operator precedence. So the binary tree is pretty much structured for operator precedence to take place correctly. There's also a Python programming language, programming lecture of a recursive descent parser. And this is pretty much it for operator precedence. It's important because some operators may have to be prioritized first and calculated or performed on before another operator is performed on. Thank you for watching. I'm Jack, your instructor for this course. I'll be going over what grammar is in terms of parsing, and this is probably one of the most important lectures. So grammar is used to describe the syntax of a programming language. So if, for example, with Python, you have to write x equals blah, 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 x equals 5. You can't say like 5 equals X, right? It's basically saying you have to structure your words uh, in order or something to create for the syntax of the programming language. If you don't quite understand, I'll be explaining more in the next slides. So here's a grammar example. They are awesome. So if you know, of course, the English language, there has to be a noun first, and then a verb, and then an adjective, right? So it can't be like they awesome are. That's grammatically incorrect. So that's what the parser will help with is it will detect that grammar and then it will error. So if the grammar is incorrect, then it is syntactically wrong. So it must be noun, then verb, then adjective, right? So here's a grammar example. So EBNF, which stands for Extended Backus Nor Form, is a way to specify a formal language grammar. It's just code to express the syntax of a formal language. And in fact, it's very helpful in terms of creating a programming language. It's not necessary to use EBNF, but it helps visualize the grammar and makes it easier to build a recursive descent parser. It also does not have to be EBNF specifically. You can make your own grammar language to visualize syntax. So here's some EBNF symbols. Not all, but like common ones are the ones that we'll be using. Definition, a rule defined, concatenation, all of the options, termination, ending a rule statement, alternation, one of the options, repetition, repeating occurrences, terminal string, characters defined, optionals, characters that are optional defined. If you're totally confused on this, I'll be giving you some more examples of how these work. You pretty much need an example before you actually understand really what these usages mean. So this is just more of a chart to kind of understand or kind of, I guess, remember, recall what these usages are. So here's a basic example of here. So favorite numbers equals to 2, 4, 5. So the line that goes straight down is alternation, right? So it can be any of the 2 or 4 or 5. So what I mean is saying, for example, so the favorite numbers can be 2, 4, or 5. It doesn't have to be all of them. It can be either one of the texts or characters. Dislike numbers, same thing. It can be 1, 3, or 6. The semicolon is just to say that, oh, the statement ends, or we just end it here. It's just creating like a new line. It's not that. You'll understand. And then both numbers, favorite numbers, the comma represents concatenation, which just means just add them together. So we're saying, and for both numbers, we're saying it has to be a favorite numbers plus dislike numbers. So look at the examples below. 3 means dislike numbers, and it's a dislike numbers because 3 is one of the options in the alternation, right? And then 4 is an option and favorite numbers, right? So it's one of the options in the alternation. And then 26 is both numbers because 2 is a favorite number, and then 6 is a disliked number. Same thing with 41. 4 is a favorite number, and 1 is a disliked number, as you see in the very definitions here. If you don't quite understand this, I understand. You're not gonna be heavily going to this with a really, really simple compiler. But it's helpful to learn. It's just easier for you to understand the grammar. Here's a more complicated grammar example is digit without zero and then digit. So digit without zero is like 1, 2, 3, 4, 5, 6, 7, 8, 9. It's basically a digit without zero, right? And a digit is just zero and that digit without zero. And then this comment will affect the code. It's just ignore that. When you put in a parentheses and a multiple or a star symbol and then a star symbol in a parentheses, just it's a comment. And comments don't really do anything to the code itself. And then number is digit without zero and then comma, concatenate, and then the brackets here will indicate that, hey, there can be as many digits as possible. It's repeated occurrences basically. So there could be one. So like here's an example: 1492. So 1 is that digit without zero, and the digit right here with the brackets is 492. The digits can repeat as much as they want in terms of character. And then 6, there is a digit. 6 is a digit without 0, and the 3 is a digit without 0. And EBNF grammar for mathematical expressions. So digit without 0, and then digit, and then natural number. This is saying, hey, this is just pretty much a number. So it can be like 612. And we make a flow where it can be a 0, or we add a possible. The square brackets mean like optional. So there can be a character, negative character or not. It doesn't matter. And then that natural number, and then a dot, and a optional dot, and then that digit. So just in case there's a decimal. And then there's a factor, which is the expression, parentheses, expression or float, or a plus and then a factor and a minus and a factor. This is just the unary operation pretty much. And then term, a factor can be a factor, and then repeated occurrence of a multiply, or a star symbol, division or modulo, and then factor. And then term, plus or minus term, pretty much the whole expression, like 1 plus 2 times 3. Pretty much if you didn't understand the EBNF grammar, this is a easier representation of it. So we have a factor, which is the 10, 20, 30. That's a factor, right? And the term is 10, it could be 10, right? Or it can be 20 times 30. That's the term right there. So you see how the colors represent like term orange right here. 20 times 30. And then expression is the whole thing. So 10 plus 20 times 30. So the term is only used for multiplication, division, modulo. The expression is used for all of the operators, like addition. Well, technically only the addition and subtraction, but it still counts in. And then the factors are just pretty much the numbers themselves. And the factors are also unary operations, so like negative 20 or something, but it's just 10, 20, 30. So now I'm going to explain what a recursive descent parser is. So it's actually a type of top-down parser. So it builds from the parse tree from the root to the leaf. And you're like, what is the root? And what is the leaf? Well, I've already explained what the leaf is. Pretty much, it's a really easy concept. So it's just, here's the root, and then here's the leaf. So it's pretty much saying like the root is the very top, and the leaf is the one with no children. And then see right here, it's just building the parse tree from the root to the leaf. So it builds it from the root, and then up until to the leaf with the ones with no children. So that's why it's a top-down parser. It's top-down because it goes from the top and it goes down to the bottom. So it uses recursive functions to understand and recognize input. That's what it does. That's why it's called recursive descent, because it uses recursive functions. If you don't know programming, you may not understand this, but if you do know programming, you will understand what recursive functions are. So here's an example of a recursive descent parser pseudocode. So there's a procedure factor, and then if token types left parentheses, we go to the next token, expression, and then right parentheses, next token, syntax error. And then, yeah, this pretty much detects the negative or positive, or if it's a number. Or if it's a left parentheses, and then we get the expression right. And the term is just pretty much the multiplication and divide. And then the modulo as well. Next token, result, multiply node, divide node. It returns the nodes. And then expression is just pretty much detecting the plus, minus. So right here like this. If you would like to go into more of the pseudocode around here, just pause the video to see more of it. And then the procedure part should be easy. It's kind of unnecessary, but you're just pretty much getting the expression, calling the expression function, and just returning it. So again, there's a Python programming lecture of a recursive descent parser. And then that's pretty much it for grammar. Thank you so much for watching. Grammar is one of the most important parts of the parser, as it defines the rule set and the rules and the structure of the language. Thank you so much. I'm Jack, your instructor for this course. We'll be going over the parser section of the compiler. So let's get started. So here are the nodes right here. We've made a number node, which will just store the value of the number value. So let's say like 5.3 or something, and we'll just return a representation of that self.value. And then we also made a binary node, which has a left node and a right node, which is the operator. So the type will be like, let's say TT plus, TT minus. So it's operating on two operands. The left node is the number and the right node is a number. Or it can be another node, for example, unary node. Just it's just operating on two, right? So a representation, we return string and then concatenate that to self.left node and then convert that operator to character. So this is why it's a useful utility function. And then right node and then parentheses, right? It is a unary node. Self.type is a type, and then there's only one node. So there's gonna be like, let's say negative or positive number. So here's an example. Right, here's representation. So now we go through the parser. So this is a recursive descent parser, and the reason why it is because it uses recursive functions. For example, we call self.term from the term, and then we recursively use it. So self.factor here, we see how it has a self.factor function right here that's being used. So it's just a recursive function. So we make an initializer and then the tokens list token. This is technically a type annotation, but don't think it's a default argument. It's not. Self.tokens equals tokens. Self.index equals 1. Basically, what we're doing the same thing. We're advancing, so we're going to the next token, and then when we call the advanced method, we go to the next token in the list. So we parse, and then if there's like any errors, it's just gonna return none. We have an expression. So we first of all we build it up with the factor. So let's say the factors are left parentheses. We advance, get the result, and then make sure that the right token, the right token has to be a right parentheses, or else it just wouldn't make sense, right? So like you say parentheses, left parentheses, 1 plus 2, right parentheses, it has to end with the right parentheses. That's why this is stating the grammar or the rule set is it has to be a right parentheses, right? That's the grammar. And then we advance and then return the result. Now it's a number, we just return a number node. Plus we actually do a unary node and then return a self.factor, so we actually call that factor again. Same thing with minus. And then one of the results is called the term, or the expression will be called from the factor. While self.current token is not node, and if it's TT plus, if it's a TT plus or TT minus, we check if it is the binary node, result in the self.term, we advance, make sure, same thing with term. If it's not, if it's in multiply, divide, or modulo, same thing here, the left, result, right, factor, advance, advance, advance. Pretty much you see how these will pretty much call each other the whole time. So it'll call this and then call this and then call this and then call this and then call this. It's just pretty much going loop and loop and loop. It's just calling all of each other at, continuously. So that's what the recursive descent parser is. That's all for this video. Thank you so much for watching. I'm Jack, your instructor for this course. I'll be going over what an interpreter is. So an interpreter directly executes instructions written in a programming language without it being compiled previously into a machine language. So pretty much an interpreter executes source code, directly executes source code, and returns the output right away. So here's what a compiler is. And trust me, a compiler and an interpreter are not the same exact thing. A compiler converts that source code into machine code, and then that machine code gets executed by that computer to generate an output. An interpreter just converts that source code, or it doesn't convert the source code, but just directly executes that source code. So then the output is given straight away or right away. So here's some commonly interpreted language: Python, JavaScript, Ruby, and PHP. Here's some commonly compiled languages: C, C++, Rust, Go, and Haskell. Python, or the C Python implementation, uses a bytecode interpreter. And bytecode is a form of instruction designed to be executed efficiently by an interpreter. So basically it's kind of like machine code, kind of, but like it's like bytecode. It's written in just very simple instructions that can be easily executed by the interpreter. Usually the interpreter is implemented as a virtual machine. It stands for VM, that executes the bytecode. So there's like stack-based virtual machine or register-based virtual machine. All those type of virtual machines. Like right here, these virtual machines like stack-based and register-based are used for bytecode interpreters. There's a Python programming language on an abstract syntax tree interpreter. Thank you so much for watching. That was pretty quick, but interpreters, in terms of an interpreter, it's not too strong of a detailed thing, especially if we're just going over the abstract syntax tree interpreter, which is a very, very easy concept. Thank you for watching, and see you in the next lecture. Hello, I'm Jack, your instructor for this course. I'll be going over what abstract syntax tree or binary tree walking or abstract syntax tree interpreter. So an abstract syntax tree interpreter walks over the abstract syntax tree and executes for each kind of expression. So think of it like just going through that tree, going through all the nodes, and then just executing operations on each node. So it just goes through each node, which means visiting, quote unquote, visiting each node, and then executes directly on those nodes. The name abstract syntax tree interpreter, it doesn't have to be an abstract syntax tree. It could just be an expression tree or a binary tree or another tree. So here's an example of walking over the tree 1 plus 2 times 3. So let's scan through this abstract syntax tree. Oh, so we have to add 1 to this multiply child node. And then 2 times 3. Oh, we see here we have to multiply 2 times 3. Oh, so that converts to 6, right? Because 2 times 3 is 6. Now we can actually add 1 plus 6, since now we have 6, which became the result from the multiply operation. 1 plus 6 is 7. And 7 is our answer. So here's a pseudocode example of an abstract syntax tree interpreter. So we visit, this is not actually the whole thing, but like this is just an example, like a binary add node. If the node is a binary add, we just return a number, visit the left child node, and to get that number value, plus visit the right child node, get that number value. Same thing with unary negative node. Oh, we know it's a negative number, so it's -1 times, and to convert it to whatever, to the negative. And then if the node is equal to number node, we just return that number node value. Right. There's a Python programming lecture on an abstract syntax tree interpreter. And that's pretty much it for what a tree walker is. It's very quick. An abstract syntax tree interpreter is very simple and very easy to make, because all you have to do is you just have to recursively visit each node and then just operate on them. Thank you for watching. The instructor for this course. The last part we'll be going over in this Python programming lecture is the interpreter. This is probably one of the easiest parts of this compiler design. The interpreter is really easy to make. So first of all, we just need to create our values. So we have a class number. Value is going to be the float, right? It's because it's a number. Then return a representation. It's just str, converting to the self.value to a string. So now we have the interpreter. So we actually use a visit function, which will return that number value. And if it's an instance, if this node is a binary node, we actually self.visit that binary node. If this instance is a unary node, then it's a unary node. This instance is a number node, and then we just return that number node.value. And then if it's an unknown node, we just raise a runtime error. So let's say we visit a binary node. If the node type is a plus, we just create a new number class or number instance. We self.visit that left node and get that value, plus self.visit right node, get that value. And it's pretty much the same for every single one of them, but with a different operator. The divide, we can't divide by 0, right? So we just create a runtime error saying the user can't divide by 0. Same thing with the modulo, can't divide by 0. And the unary node, we're just pretty much adding positive or negative to it right here, like this. That is what the unary will do. We get that value when we visit the node and then convert it to whatever it's needed to be converted to. That's pretty much it. We know that this visit is going to left the node, for example. So if it has to do some more calculation or visit the binary node again, then we can do that, right? But yeah, this is pretty much it. We just recursively call the visit function. Like let's say the left node is a number. Then the number, or let's say the left node is a unary node. And then it'll say it's a visit unary node. It'll go back to here and then convert it to, let's say, a number, right? So let's say it's a negative unary negation and then -1, right? And then it'll return that number value back here, right? And then it'll add it with the correct values and stuff. In interpreter, we go back to our main file, and then of course we get the lexer, we get the tokens from that lexer when we generate from the text, and then we use the parser, add in the tokens, and then get the tree from those tokens from the parser, so parser.parse. And then if the tree is none, just continue. So, or yeah, pretty much continue the while loop on top. And then if the tree is not empty, then we get the interpreter, we visit that tree, and then we can just get the value and print the value, which is our result or our interpreted value. So that's pretty much it for this. Thank you. Anyways, thank you so much for watching, and hope you go to the next and last section of the summary and final. Your instructor for this course. I will be going over the whole course of the basic compiler design. This is essentially the summary of the whole course. So I will begin. So what is a lexical analyzer? So what we've learned is that the lexical analyzer converts a sequence of characters or text into lexical tokens. So let's say we have 2 plus 3. It converts with the lexical analyzer, it converts into a sequence of lexical tokens. And those tokens will be like a token number value of 2, and then the next token would be a plus sign, and then the next token would be a number of value 3. That will be the tokens that are generated from the lexical analyzer. This pretty much sets up a lot of data and what each purpose of the token is. So therefore, the parser can understand these tokens and have a better idea of how to create a abstract syntax tree or a parse tree. And then next step is the parsing step. Parsing takes input data and builds a data structure, usually an abstract syntax tree or parse tree based on a rule set called grammar. So there's grammar within the parsing, where basically these tokens or values must be in correct order. Like let's say 1 plus 2, it can't be plus 1 plus, for example. That would be incorrect, and that would have the wrong grammar, which will create an error, of course. So it's based on a rule set called grammar, and also it creates a parse tree or an abstract syntax tree, and that tree is going to be used to then be used in the compiler or an interpreter. But this is one of the most complicated steps, or one of the really necessary steps to be able to create a compiler. The abstract syntax tree will create roots, parent nodes, child nodes. It will also help with the order of operation or operator precedence, because we know which which node to execute first. We need this type of node to do another operation. It's very helpful. And an interpreter is the step after after parsing, or the step the interpreter or compiler is a step after parsing. The interpreter basically executes instructions written in a programming language without it being compiled previously into machine language. So what will the interpreter do is, let's say we have like 1 plus 2, it directly executes that code and it returns 3. You can think of Python or C Python as an example of an interpreted programming language, where you enter code and then it directly executes that code and returns a result for you. So yeah, that is what the interpreter is. And an abstract syntax tree interpreter is the one that I've shown you what they are. We just walk over the tree and visit each node, and it executes each node by there. So a compiler, it can the actions written in a programming language into machine code or lower level form. So what a compiler does is it converts that source code into machine code, like assembly or binary, where that can be easily read and easily seen by the computer or by our computers, and then our computer can pretty much execute that binary or that assembly code easily. So the reason why a compiler is more of a multi-step kind of thing is because it has to convert that source code into machine code, and then you have to execute that machine code by the computer. Whereas the interpreter, it just automatically or directly just executes that source code, which can make it more convenient depending on a person. But that's why, for example, like shell scripts, they're interpreted, so it pretty much makes it so we can easily create some code and then easily quickly execute that code. So yeah, so the difference between a compiler and an interpreter is a compiler converts that source code to machine code, but the interpreter directly execute that source code. So essentially, the compiler has more steps to do than an interpreter. So here's the steps of the process. We have the source code, and then we go put that source code into the lexical analyzer, and then after the lexical analyzer, it goes into the parser. From the lexical analyzer has like the tokens, lexical tokens, and it goes to the parser where that parser converts those tokens into the parse tree or abstract syntax tree, and then the tree gets sent to the compiler interpreter, and then the tree is used to execute the source code or convert it to machine code. Here's an example of 1 plus 2 times 3. So what the lexical analyzer do is it will generate this many tokens with token type number 1, token value 1, and then token plus, token number 2, and then token multiply, and token number 3. It's in the correct order, so it's ordered correctly to 1 plus 2 times 3. Remember token value with NA, we already have enough data or information that's a plus sign. Like right here, it clearly says it's a plus sign. It's nothing else. And then the parser, what it does is it converts those lexical tokens into this tree or expression tree or parse tree. We have the add first, add operation, number value 1. And then we go into the multiplication operation, which is number value 2 and number value 3. Remember, with operator precedence or order of operations, we see here 2 times 3 is lower, and so it makes it so that in order to do this addition, we need this multiply operation first for it to work. And then now we have to walk over this tree, which is within the interpreter step or abstract syntax tree interpreter. So we see that this is an add operation, and in order to add 1 plus this, we have to multiply this first in order to be able to add this, right? Do multiplication first, so 2 times 3, and then this becomes 6, and then now after that we do 1 plus 6, and then it becomes 7. So we here 1 plus 6 and then 7 here. So that is pretty much it of basic compiler design. We go through the lexical analyzer, then to the parser, and then to the interpreter. Thank you so much for going through this whole course and looking over a lot of these lectures. It's a pleasure to have you here and listen to my lectures. And thank you so much.